What you are about to hear is the universe screaming into existence. This is actual data from the cosmic microwave background, the oldest light in the universe, converted into sound. When scientists used advanced AI to analyze this reconstructed sound, they found patterns that shouldn't exist, alignments that defy explanation, frequencies that are missing when they should be there. This sound carries secrets from 13.8 billion years ago, and some of those secrets remain unexplained. 13.8 billion years ago, the entire universe erupted from a single point in an event we call the Big Bang. Everything that exists today, every atom in your body, every star in the night sky, every distant galaxy, began in that singular moment of creation. The Big Bang was the explosion of space itself. In the first fractions of a second, the universe expanded faster than the speed of light in a process called cosmic inflation. The temperature was unimaginably hot, around 10 to the 32nd degrees Kelvin. Matter as we know it couldn't exist yet. Instead, the universe was filled with a roiling soup of fundamental particles, photons, and pure energy. As the universe expanded, it cooled. Within the first 3 minutes, protons and neutrons formed and fused together to create the first atomic nuclei, mostly hydrogen and helium. But atoms themselves couldn't form yet. The universe was still too hot, too dense. Photons constantly collided with free electrons in an endless dance of scattering. Light couldn't travel freely. If you had been there, you couldn't have seen anything, because photons were trapped in this cosmic fog. For the next 380,000 years, the universe continued expanding and cooling. Then, something remarkable happened. The temperature dropped to about 3,000 Kelvin, cool enough for electrons to bond with nuclei and form stable atoms. This moment is called recombination, and it changed everything. With electrons locked into atoms, photons suddenly had nothing to scatter off of. For the first time in the universe's history, light could travel freely through space. The photons released at that moment have been traveling through the expanding universe ever since. As space stretched, those photons stretched with it, their wavelengths growing longer and longer. What started as visible light has been redshifted into the microwave region of the electromagnetic spectrum. Today, we call this the cosmic microwave background radiation, and it fills every cubic centimeter of space. This is the afterglow of the Big Bang, and it's what scientists use to reconstruct the sound you just heard. Here's something that might surprise you. Before those first atoms formed, the early universe could actually carry sound. These were real acoustic waves, actual pressure oscillations traveling through the cosmic plasma. In the first 380,000 years after the Big Bang, the universe was incredibly dense. Baryons, which are particles like protons and neutrons, were tightly coupled with photons through electromagnetic forces. This created a plasma that behaved like a fluid. When dark matter began clumping together due to gravity, it created density fluctuations in this baryon-photon fluid. These fluctuations set off pressure waves, sound waves, that rippled through the entire universe. The physics here is straightforward. Sound is a pressure wave moving through a medium. In air on Earth, sound travels at about 340 meters per second. In the early universe, sound moved through the baryon-photon plasma at about 60% the speed of light. That's roughly 180,000 kilometers per second. The wavelengths of these cosmic sound waves were enormous, spanning hundreds of thousands to millions of light years. The largest coherent oscillations that had time to develop before recombination reached about 230,000 light years across. There simply wasn't enough time for anything larger to form oscillations before the music stopped. When recombination happened and atoms formed, the electromagnetic coupling between photons and baryons broke. The pressure supporting these waves disappeared almost instantly. The oscillations froze in place, imprinted forever in the temperature fluctuations of the cosmic microwave background. What we observe today as tiny temperature differences in the CMB, just millionths of a degree, are actually snapshots of those frozen sound waves from the universe's infancy. The pattern of these waves tells us extraordinary things about the early universe. The peaks and valleys in the CMB power spectrum represent different harmonics, like the overtones in a musical instrument. The first peak corresponds to regions that had just reached maximum compression when recombination happened. The second peak represents regions that had compressed and then expanded back out. The third peak captured regions that had compressed, expanded, and compressed again. These acoustic peaks contain precise information about the density of ordinary matter, and dark energy in the universe. Turning ancient light into sound required transforming data in ways that preserve the physics while making it perceptible to human ears. John Cramer, a physicist at the University of Washington, pioneered this approach starting in 2003. Using data from NASA's Wilkinson Microwave Anisotropy probe, he updated his work in 2013 using even more precise data from the European Space Agency's Planck satellite. The cosmic microwave background exists as a map of temperature fluctuations across the entire sky. The Planck mission measured these fluctuations with extraordinary precision, breaking them down into multipole components. Each multipole represents oscillations at different angular scales. Low multipoles correspond to large-scale patterns spanning much of the sky. High multipoles represent small-scale ripples. These multipoles are essentially the frequency spectrum of the early universe's acoustic oscillations. Cramer took this frequency spectrum and converted it into sound waves. He assigned each multipole a corresponding audio frequency, creating a sum of sine waves that represents the combined oscillations. But there's a problem. The actual frequencies of these cosmic sound waves are absurdly low. The wavelengths spanned hundreds of thousands of light years, which translates to frequencies far below anything humans can hear. To make this audible, Cramer had to scale the frequencies upward by a factor of about 10 to the 26th power. That's shifting the cosmic bass into the range where human ears can detect it. The reconstruction also accounts for the expanding universe. As the universe grew during those first 760,000 years, it stretched like a bass instrument with loosening strings. The sound frequencies dropped as space expanded. Cramer's simulation models this by having the component frequencies shift downward over time, following the predictions of cosmological expansion. The sound rises in intensity, peaks at around 379,000 years after the Big Bang, when recombination was at its maximum, then fades as the process completes. This is where modern artificial intelligence enters the picture. While Cramer's original work used traditional physics calculations and Mathematica programming, researchers today are deploying sophisticated machine learning algorithms to push this analysis further. Neural networks can now process cosmic microwave background data in ways that were impossible just a few years ago. Scientists have developed graph-based Bayesian convolutional neural networks, specifically designed for CMB recovery. These AI systems can clean the CMB signal by removing contamination from foreground emissions, like dust, in our galaxy. They predict cleaned CMB sky maps with pixel-by-pixel uncertainty estimates, something traditional methods struggle with. The AI doesn't just clean the data. It learns the underlying patterns and can identify features that might indicate new physics. Other teams are using neural networks for cosmological model selection. These AI systems can examine the power spectrum of the CMB and determine which theoretical models best match the observations. They can distinguish between different inflationary scenarios, different compositions of dark matter and dark energy, and even detect subtle deviations from our standard cosmological model. The AI analyzes thousands of parameters simultaneously, finding correlations and patterns that would take human researchers years to uncover manually. Physics-informed neural networks represent another frontier. These combine the pattern recognition power of deep learning with fundamental physical laws. They can solve complex differential equations that describe how sound propagates through the early universe, predict how gravitational effects distort the CMB signal, and model the formation of large-scale structure. Machine learning is revolutionizing acoustics research across many fields, and cosmology is reaping the benefits. This is where the story gets genuinely strange. When scientists analyze the reconstructed sound and the underlying cosmic microwave background data, they keep finding anomalies, features that shouldn't be there. according to our best models of the universe. Patterns that have been confirmed by multiple independent experiments, yet remain without satisfactory explanation. The most famous mystery involves the quadrupole and octupole. In the language of spherical harmonics, these are the lowest multipoles, corresponding to the largest angular scales in the CMB. Think of them as the deepest bass notes of the cosmic sound. According to the standard cosmological model, these should be randomly oriented relative to each other, and to any structures in our local solar system. But they're aligned in a way that defies reasonable explanation.
The quadrupole and octupole are aligned with each other. They're also aligned with the ecliptic plane, which is the plane of Earth's orbit around the Sun. They show alignment with the equinoxes. These are patterns from 13.8 billion years ago, frozen into the structure of space-time when the universe was just 380,000 years old. Why would they correlate with Earth's position and motion? Some scientists suggest this could be the signature of quantum corrections or new physics, operating at the largest observable scales. Others suspect systematic errors or foreground contamination that hasn't been properly removed. But the Planck satellite, which is far more sensitive than previous missions, recorded the same anomaly. Instrumental error appears ruled out. Then there's the mystery of the nearby galaxies. Recent observations have revealed something completely unexpected. The cosmic microwave background temperature is significantly lower in the direction of nearby large spiral galaxies. This temperature decrement extends outward from these galaxies to distances of several megaparsecs, far beyond the visible extent of the galaxies themselves. The effect has been confirmed at the 5.7 sigma level of statistical significance. In physics, 5 sigma is the gold standard for discovery. This is real.
What makes this truly mysterious is that no known physical mechanism can explain it. Secondary anisotropies like the Sunyaev-Zeldovich effect can alter CMB temperatures around massive objects, but those effects have well-understood signatures and don't match what's being observed. The temperature profile around these galaxies is smooth and extends much farther than any conventional explanation allows. Some researchers have speculated about unknown interactions with CMB photons, possibly involving dark matter halos around galaxies. Others wonder if this represents a completely new foreground component that we've never accounted for in our models.
This galaxy CMB correlation might actually explain several other long-standing anomalies. For years, researchers have noted that the power spectrum at the largest scales is lower than predicted. The universe's deepest notes are quieter than they should be. There's also a hemispherical power asymmetry, where one half of the sky shows considerably more fluctuation power than the opposite hemisphere. The famous cold spot in the southern galactic hemisphere, an unusually large cold region that has puzzled cosmologists for years, sits precisely at the location of the only large group of spiral galaxies within 100 megaparsecs. When researchers modeled the unknown temperature profile around these galaxies, it produces a structure matching the cold spot's position and characteristics. There's more.
The distribution of matter in the universe shows an unexplained correlation with CMB temperature patterns. Cross-correlation analysis reveals a significant connection between the CMB and the projected matter density field from nearby galaxy surveys. This correlation exists at distances below 50 megaparsecs and shows up with less than 1% probability of being a statistical fluke. The CMB is supposed to be a snapshot from the early universe, encoding information from recombination. Local matter distribution reflects the universe today. These shouldn't be strongly correlated unless something is creating a connection that our models don't account for.
Statistical analyses of the CMB also reveal topological anomalies.
The number of cold spots in the temperature map is anomalously high compared to simulations. The wavelet coefficients at certain angular scales show excess kurtosis. Local estimates of the angular power spectrum indicate patterns that violate the cosmological principle, which states that the universe should be roughly the same in all directions. Some physicists have proposed that these anomalies might indicate non-trivial cosmic topology. Perhaps the universe has loops or exotic structure that we haven't detected. If the universe wraps back on itself in some way, light from the CMB might travel along multiple paths, creating the interference patterns we observe as anomalies.
Machine learning algorithms are now being proposed to search for these topological signatures. The computational demands of searching for matched circles in the CMB, which would indicate light that has traveled multiple paths around a finite universe, are enormous. Traditional methods can't efficiently mine the data for these patterns. AI systems might finally give us the tools to detect whether our universe has exotic geometry. These mysteries force us to confront fundamental questions about the cosmos. Are we seeing evidence of new physics beyond the standard model? Are our cosmological assumptions wrong? Or are there prosaic explanations we simply haven't discovered yet? Some theoretical physicists are exploring loop quantum cosmology as a potential answer. This approach applies quantum mechanics to the geometry of spacetime itself. In loop quantum cosmology, the Big Bang singularity is replaced by a quantum bounce from a previous contracting phase. This theory predicts specific modifications to the primordial power spectrum that could produce the observed large-scale anomalies. It suggests that quantum gravitational effects, usually only relevant at the Planck scale, might have left detectable imprints in the cosmic microwave background. Others propose that cosmic inflation, the rapid expansion in the first fraction of a second after the Big Bang, might have had features we don't understand. Perhaps there were brief interruptions in inflation, or transitions between different inflationary phases. These features would create oscillations, or bumps in the primordial power spectrum. When researchers model inflation with these features, they can reproduce some of the observed anomalies. The challenge is determining whether these models are physically motivated or just mathematical exercises designed to fit the data. The hemispherical asymmetry and alignment problems might also point toward violations of fundamental symmetries. The cosmological principle assumes the universe is statistically homogeneous and isotropic at large scales. The anomalies suggest this might not be strictly true. Perhaps the universe has a preferred direction, breaking rotational symmetry. This would be revolutionary, overturning assumptions that have guided cosmology for nearly a century. The galaxy CMB correlation presents a different kind of puzzle. If confirmed and understood, it might reveal new aspects of how matter and radiation interact. Dark matter halos could have properties we don't currently comprehend. There might be exotic particles or fields that mediate interactions between ordinary matter and CMB photons. Or this could indicate that our understanding of cosmic expansion on local scales needs refinement. Whatever the explanation, these anomalies represent opportunities. Science advances fastest when observations challenge our theories. The cosmic microwave background has already given us precision cosmology, allowing us to determine the age, composition, and evolution of the universe with remarkable accuracy. Now, it's presenting us with puzzles that might lead to the next breakthrough. The next generation of cosmic microwave background experiments promises to bring unprecedented precision to these questions. The Simons Observatory, currently under construction in Chile, will survey the CMB with far greater sensitivity than previous experiments. Lightbird, a Japanese-led satellite mission scheduled for launch in the late 2020s, will focus on detecting primordial gravitational waves through their signature in CMB polarization. CMB-S4, a proposed ground-based experiment in Antarctica, aims to deploy over 500,000 detectors to map the CMB with exquisite detail. These experiments will measure the CMB polarization with precision that could finally settle many of the current anomalies. They'll probe the inflationary epoch with enough sensitivity to detect or rule out various theoretical models. They'll map the large-scale structure of the universe through gravitational lensing of the CMB. And they'll do all this while generating data sets of unprecedented size and complexity. This is where artificial intelligence becomes essential rather than optional. The data volumes from these next-generation experiments will be staggering. Traditional analysis methods won't scale. Machine learning systems will clean the data, identify systematic errors, extract signals buried in noise, and test theoretical models against observations.
AI will enable discoveries that would be impossible through human analysis alone.
Researchers are already developing neural networks that can simulate the cosmic microwave background faster than traditional physics codes. These AI emulators learn the relationship between cosmological parameters and observables, then predict CMB spectra almost instantaneously. This allows scientists to explore vast parameter spaces, testing thousands of theoretical models to find which ones match observations. It accelerates the entire scientific process. Some teams are training AI systems to recognize specific patterns that would indicate new physics. Neural networks can learn the subtle signatures that different types of dark matter would leave in the CMB. They can identify the fingerprints of modified gravity theories. They can even predict what observers would see if the universe has exotic topology or extra dimensions. By training on simulations representing all these possibilities, AI systems become expert pattern recognizers, capable of spotting the faint traces of new physics in real data. The combination of better data and smarter algorithms means we're entering a golden age for understanding the universe's birth. The sound of the Big Bang, reconstructed from cosmic microwave background data, will become clearer and more detailed. We'll hear harmonics we've never detected before. We'll understand the physics that created each note and frequency. And perhaps we'll finally explain the anomalies that currently defy our understanding. The mysteries in that sound, the unexplainable patterns we've discussed, might soon make sense. Or they might lead us to even stranger realizations about the nature of reality. Either way, we're listening to the universe's first cry. And it has stories to tell that we're only beginning to understand.